Hello everyone. Today we're going to be talking about pages 6 through 8 of your notes. So pull those out, and just like we would in class, if there's a practice problem, fill it in. If you need to add to your notes at all, if I say something in a different way that's helpful, then add those to your notes. But today we're going to be talking about understanding reaction rates through a graphical analysis. Okay, so we're going to start on page 6. If you hear doggy noises, I'm sorry about that. I have my 3 dogs here with me. So, reaction rates and understanding them graphically. So first thing I want you to notice when you look at this graph, we typically have concentration in the y direction and time in the x direction. And so time as we see this reaction occur from where it begins to where it ends. Okay? Notice that at the beginning of the reaction at time 0, our concentration of products is 0. And that should logically make sense to us. If we initially start a reaction, then there shouldn't be any products. But then as time passes, the concentration or the amount of product increases, but then we get to a point where it tapers off because we're no longer making products. We've completely run out of reactants. Reactants all went to 0. And if we don't have any reactants, then we can't be making any more products. Sometimes these graphs have just the products, but occasionally we also include the reactants. So be very clear and check on which one is which. Make sure that you're looking at the correct line and if that is reactants or products. Okay. So what do we notice about the slope of the graph? Well, slope would be rise over run. So that would be concentration over time. And if we're just looking at a little chunk of time, then that would be a change in concentration or a change in amount over a change in time. And we should recognize that as the rate of reaction equation, a change in concentration over a change in time. So the slope of this line is the reaction rate. Are they linear? No, it looks like they have a curve to them. And why do you think they behave that way? Why are they not linear? Let's think about that. Well, if we look at this graph, we're starting off with a very steep slope, and then as we get to the end here, we have a very shallow slope. So we have a high rate of reaction, and then a slow, low rate of reaction. So in this particular reaction, I would say in most of them, it starts off very quickly. Lots of products are being made, but then as time passes, we get less and less products created, and logically that makes sense. Okay, so you can measure the disappearance of reactants. Reaction rates and how graphical analysis benefits us. So we have our reactant, and then we have 2 products. And so we see that the concentration is all reactant, and we don't have any product at the beginning of the reaction. Okay? And so we can see here that our reactant is disappearing, and our products are appearing. They're being created. Okay? But why would our nitrogen monoxide, why would we have more of those than our oxygen gas? If they're both reactants, then why do we end up with more nitrogen monoxide than our oxygen gas? And the reason why is because it's proportional to these stoichiometric values. We know that for every 2 carbon dioxides, every 2 of those, we will end up with 2 nitrogen monoxide and only 1 oxygen gas. And so when I look at that, we go, oh, well, if we have 2 of those, then we're going to have 2 of these, and we're only have 1 of those. There's going to be half as much oxygen as there is nitrogen monoxide. Okay. Like we said, reaction rate is the slope of this line. And so when the slope is the steepest, think of this like a hill. You're pedaling your bike up a hill. And for the products where we're increasing in concentration, where it's the hardest to pedal, where the hill is the steepest, that's when the reaction is going the quickest, because the concentration of product is being created more quickly. Now it's starting to slow down, and then when our slope is now flat, we're no longer creating product, and so the reaction has come to a stop. Okay, so we have our reactant in purple, and we have our product in green. So which curve represents the product and which represents the reactant? If that's not on your graph, I want you to add this to your graph in your notes. Which one's reactant and which one's product? And then off to the side, explain how you know that's the reactant and how you know that's the product. And then where is the rate the fastest and where is it the slowest? Well, our last slide told us when the slope is the greatest, or it's the steepest, that's the fastest, and then where it's the most shallow, that's where it's the slowest. So at the beginning of the reaction, our slope is steep, so that means that the reaction rate is going quickly, and then we end here, and our slope is very shallow, and so that's where it's really slowing down. Okay, let's go through a couple questions and test our knowledge. So when you look at this graph, which experiment shows the fastest reaction rate? Is it A or is it B? And take a moment, hit pause, get this down in your notes, and if you already have the answer, then I want you to explain the answer in your notes. The correct answer is A, but how do we know this? Well, when we look at the slope of the line, which would indicate the reaction rate, we see that the slope is much steeper. We have a greater slope, and so that means a faster reaction rate. So that's why A has the fastest reaction rate. Now we can compare values. We can look at 2 seconds. So they both started at 0, which would mean that they're the product, not the reactant. The reactant isn't shown here. At a time of 2 and value in seconds, A has 15 volume of gas in cubic centimeters, so 15 cubic centimeters, and then we only have 10 cubic centimeters for B. An experiment was run using the same reaction, so these are not different types of reactions, they're exactly the same, but with different amounts of reactants. Which experiment uses more reactants, B or C? Okay, write down what you think in your notes. Let's talk about it. The correct answer is C, and here's why. When we use up all of our reactant, then we've maxed out on product. Okay? And so for B, we're ending at about 20 cubic centimeters-ish. Okay? Oh, are we saying 24 here? Okay, somewhere in that range. And for C, we end with a higher amount, closer to 25 or 30. And so that means we had to start with more reactant in order to gain that much product. Okay, which part of the reaction rate graph shows the reaction slowing down because we're running out of reactants? Which part shows that the reaction has stopped? And then which part the reaction is happening the fastest? So get those answers in your notes, hit pause. Okay. So when I look at this, I'd say, well, where it's the steepest is where it's happening the fastest. So A would be part 3 here. Okay? And then the reaction having stopped, and we're no longer creating products, so that would have to be C. And then where it's slowing down, we're getting less steep, that would be B. Okay, so now you've reached page 8 of your notes, and this is what's due this week. You need to finish page 8, and we need to get that turned in on Canvas this week. Okay, and the Getting Started video explains how to get that turned into me, but you're going to be going through 7 questions on there, getting it all filled out either on your hard copy or digitally and turning that in on Canvas. So you're going to go through and answer what are the 3 elements that make up collision theory. You're going to talk about activation energy. How does a catalyst work? You're going to label the diagram, and then you have a couple more questions that you're going to be answering. Okay, guys. Well, I'm excited to see you all at our Google meeting this week. I'll email you about that today and give you times and the link. And if you have any questions at all about this material, please send me an email and I'll get right back to you.